Hello, everyone, and welcome to this edition of the Cineca webinar series, where we have with us Case van Bokove, which will present Introduction to FAIR Principles, Open Science through FAIR Health Data Networks, Dream or Reality? My name is Marta Lloret. I'm involved in Cineca on behalf of MBLBI, and I'll be hosting this webinar today and manning the question function at the end. I'd like to make you aware that this webinar is being recorded, including the question session. The recording and the slides will be available to you on the Cineca website and on the YouTube channel. At the end, we have reserved some time for question and answers, so questions from the audience. You can ask your questions in the question box in the GoToWebinar application. I will briefly introduce the Cineca project. Cineca stands for Common Infrastructure for National Cohorts in Europe, Canada, and Africa. It's a 4-year project funded by the European Union's Horizon 2020 program and the Canadian Institute of Health Research. Cineca's vision is to accelerate disease research and improve health by facilitating transcontinental human data exchange. To do this, Cineca works on several challenges. The first one is federated data discovery. So how, as a researcher, you find cohorts of interest, and this could be for a specific genotype or phenotype. And then once you find the data, how do you get permission to access it? So Cineca is working on an interoperable authentication and authorization infrastructure. And once you find the data and want to ask questions across cohorts, there's a need for a harmonized cohort level metadata. And the ultimate aim is to enable federated data analysis for research and healthcare applications. So Cineca works with a set of demonstrators across cohorts in both research and clinical settings. And above all these challenges, there's a fundamental need for a harmonized transnational ELSI framework to address the ethical, legal, and societal issues. Cineca has also an outreach and training program to increase awareness and capacity building in these areas. This webinar today is the introduction webinar to the event How Fair Are You?, which includes a webinar series and a hackathon where we will provide background knowledge and practical advice to facilitate the implementation of FAIR approaches. So the webinars after this introduction one will focus on a specific context like cohort data or software tools. And at the end of April, we'll have a hackathon, which will be a practical event where we'll work on the implementation of FAIR principles in 3 parallel streams: cohort data, software, and training materials. If you want to learn more about the whole series and the hackathon or register to it, you can visit our website. Today's speaker is Case van Bokove, and is the founder of The Hive, a company dedicated to the support and facilitation of open source, open standards, and open data in biomedical informatics. He studied computer science at the University of Utrecht and bioinformatics at VU University Amsterdam. Case has been involved with the FAIR movement since the initial Lawrence workshop in 2014 and was one of the initiators of the FAIR implementation working group in the Pistoia Alliance, hosting a formatory Pistoia workshop on the implementation of the FAIR principles in pharma research and development at the Hive in 2018. He actively contributes to international dialogue about the application of biomedical data standards such as GA4GH. Nowadays, Key's main expertise and engagements are as principal consultant advising pharma companies, academic hospitals, as well as patient and health data networks on their FAIR data strategy, and advising and leading implementation projects with teams from the Hive. At this point, I will hand over to Kees.
Thank you, Marta, for that introduction and for giving me the honor of kicking this off. So yeah, the topic is open science, as you introduced, and you already gave a great introduction of kind of my background, but my interest in open science to just underscore that a little bit, the mission of the Hive is actually to enable open science, and it has two aspects here. So one is open source software and solution, and the other one is verifying data. And these themes come back in all the projects that we participate in, Seneca being one of them, an important one for health data cohorts, but we also participate in quite a few other European and IMI projects, such as Pioneer for prostate cancer, Big Data at Heart for cardiovascular disease, Eden, which I'll briefly also comment about in this webinar, and a number of others. And open source software is often backed up by open source communities, such as the Global Alliance for Genomics and Health. So I see these working together. Before I start with the actual topic, I want to quickly take you back to frantic time in science, which was the first wave of the coronavirus pandemic last year. Maybe you remember it. There was so many research going on this new disease and also this new virus that we have never seen before in the population. And an example was the interaction with hypertension medications, such as you can see here. So what happens is very typical. You get a report that, hey, actually this class of medicine may increase the risk of COVID-19. But then there were also biomolecular modelers that said, well, based on what we see from pathways and what we know from molecular biology, we actually think that this class of drugs, angiotensin receptor blockers, could have a positive effect and maybe saving life. And indeed, the same news service a week later says that, well, now we see evidence that these hypertensive medications may improve the prognosis of COVID-19. So how do you find truth, and what should be the right scientific method to address this at scale? I will come back later to this topic and even this specific example. But for now, let me give you the outline of the presentation. I would like to start with making the case for fair and open science, and then posit that medical evidence, in my view, is really changing through open science. Finally, I also would like to give you a case study for that. Now, I know that today's audience and every one of you may have different levels. Some of you may be very familiar with the concepts like fair and open science, and for others it may be new. So what I will try to do is have a mix of the more basic coverage, what is it, and especially reference the sort of key papers and resources for that, but also try to keep it interesting for experts by introducing hopefully some new material. So for the first topic, the introduction of open science, I'd like to say that science is broken, but I don't want to be pessimistic. So I also say I think it can be fixed. So why do I say that science is broken? To underscore that statement, I just will give a few examples. One example is what's happening with postdocs. So the majority of postdocs in the US, but I think this is globally a phenomenon, is in life sciences. And if you look at the salaries, now, again, these are US salaries, but just look at the ratio between postdoc and sort of tenure and non-postdoc, you see that postdocs make way less money. And this is because there is, almost a market effect where postdocs there are too many for all the work that needs to be done. And so what you get is this sort of race to the top, which is not beneficial for science, because people get rewarded on writing grant proposals, having the right connections, and not on the academic output per se. And you see a similar thing with scientific discourse, where maybe it used to be, or the idea was originally for a journal that it was just a reflection of the dissemination or of what people talked about in scientific congresses, for instance. But now it's become this race where everyone wants to publish in a high impact journal, and you want to publish as many articles as possible to get your impact factor high. But with everyone vying for the same sort of top tier journal, you get this whole period, which I'm sure if you're in science are familiar with, of going to one journal and being rejected, and then shopping until finally half a year later, or sometimes even much longer, your article is finally published. And another by effect of this, let's say, busy science market, so to speak, is that the bias for publication leads to hasty science, or even science which uses unhelpful terms. So this paper was very popular in 2019, where the authors essentially said, let's not use the term statistical significance anymore, because it does more harm than good. So that's, goes into p-value hacking, and when is something really interesting to publish, and when does it add to the field? Another problem for science, and this is really largely sort of comes about from the scale of the science that we have today, is that it's very hard to get data. This picture, which is from the book here by Barend Mons, which is one of the founders, I would say, of the FAIR movement, and that book, which has a lot of input from his colleagues here in the Netherlands, speaks about some of the problems and has these nice pictures. And one of them is, if you want to get supplementary data, and this is definitely true for medical journals, it's hard. You have to download supplementary data PDFs. If you're lucky, you can extract something from it. Often the context is unclear. And so it's really hard to reproduce the science that you read. Now, the FAIR principles are a way to set a technical solution for some of these problems. Again, that book by Barend Mons goes in much detail. I can only scratch the surface here, and I won't go through all the 15 principles necessarily one by one. They've been published in this article. But what I do want to provide is a slightly newer angle on the FAIR principles, which is fair digital objects. So first of all, the principles themselves, as I said, they're 15, and they ask that you, when you provide data or you generate digital artifacts, you make sure that they have a globally unique persistent identifier, so that it can be unambiguously referenced from anywhere else in the world. And also that you provide metadata, so that's clear, who is the author of the paper or the data set, but also how was it generated, what was maybe the workflow used to generate data, if it's a computational result, or what was the protocol used for the study, if it's a clinical study, for instance. It also asks that data are registered or indexed somewhere in, for instance, one of the EBI EMBL resources. EBI has a great collection for that, and so has NIH and many organizations in the scientific world. So the findability aspects and the accessibility aspects, so making sure that you actually can get to the data and that there are no barriers there. The interoperability, making sure that there is a standard that you use, that other people can easily, for instance, in their software, interpret via a library, without having to first buy a piece of software, for instance, to be able to read those data sets. And to make sure that you use terms that are clearly defined and vocabularies that are themselves fair. And finally, also the reusability, so that even if the data is findable, accessible, and not interoperable, you can actually reuse it. So, for instance, that there is a clear license and that it's clear how it was generated. These all come together in the concept of a fair digital object. So it's just another way of looking at these more technical aspects of the FAIR principles, where we have the object itself, which could be a piece of software, for instance, an analysis pipeline for mapping RNA reads. But it could also be a protocol, for instance, for a clinical trial. It could be a data set. Let's say it's measurement of how well an antibody ties to a certain receptor. It could be anything really, data, code, or other research output. But one challenge I think that people sometimes overlook is that there can be many levels at which you can decide to publish your object. And so this is already the first important challenge. If you have a publication, it's clear that you're talking about a publication, but inside that publication, you may have a protocol, you may have several data sets which are linked. And so choosing this digital object container is an important part. And then on that level of the digital object that you publish, you also then need to make sure that the FAIR principles are followed, so that there are identifiers which are ideally minted by an authoritative source. For instance, for a person, often the source that's used is ORCID. ORCID generates identifiers for scientists throughout the world. And of course, it's important that not only there is an identifier for the data set and metadata, but also standards and code. So these things, identifiers, standards of code, and metadata that explain sort of the context of the code or the software or whatever the digital object is, are all very important aspects of fairness. All right, but how does this really relate to open science? Because also one of the critiques that you could make of the original paper or the FAIR principles themselves is that they are fairly technical, but they really stand in a tradition of a much broader movement towards data stewardship. And the data stewardship movement, again, is linked in with open science. So one way to define open science and how I like to look at it is by saying that if you think about the scientific process, there is a typical cycle where researchers go through, right? So you prepare your research, which is organizing your project, then you procure all the data, either by getting data that was already generated earlier or by producing new data, then analyzing the data, then sort of interpreting the analysis, writing the code and putting it nicely into a publication, making visualizations and summaries, and finally outreach by presenting this in fora, in webinars, at meetings, etc. And then the cycle goes again. That cycle in open science can only really work if it's distributed. And for instance, the FAIR principles can help us to make sure that you can indeed distribute all these activities over a large team that doesn't even necessarily need to be in one project. For instance, as a scientist, I could focus on just the discovery aspects where I only produce high quality data sets. You know, a very typical example would be X-ray crystallography, because there's a lot of effort that goes into that. But even when you're just doing a simple lab analysis or you're just doing questionnaire, it's very useful to make sure that this data is fair so others can use it. And indeed, if you then go to analysis, you know, there are bioinformatic labs these days, for instance, that do nothing else than just analyzing data sets that are already out there. And that is thanks to the fairness of these data sets, because if that data wasn't findable and accessible and interoperable, the reanalysis by other groups couldn't happen. And so this process allows us to deal with 21st century science, where it has become so complex that sometimes scientific papers have hundreds or even thousands of authors. But it's even broader than that. It's not just the efficiency improvement in science and dealing with the scale of data and collaboration. It's also a link to society. And this became very clear, I think, in the COVID-19 pandemic, where at least here in the Netherlands, I think also in other countries, there is a link between the government's policy on combating the virus and the underlying scientific research that explains why this or that would be the best course of action. And if that is the position that you have as a scientist, you can no longer afford to, be in your traditional ivory tower, so to speak, and just do your own thing in a nice academic environment. I mean, that is very valuable, but increasingly there is a direct link to society. And then it's not good enough to only do science the way we are used to do it in our own circle. We need to explain to society and to citizen scientists, for instance, to scientists from other disciplines, to data scientists that participate in hackathons and maybe are very good in the data science part, but are new to the academic discipline, what we're doing and how we're doing it. So there comes in fair data and software, but also transparency, explaining your work, thinking about the societal impact of it, and the reward schemes. This goes back to my earlier point of, are we really optimizing for the right thing in science? All right, so that's the case for open science. As I've explained, and I'm very happy to have some sort of critical questions or remarks when we get to the Q&A part. The classical way of doing science has too many perverse incentives. And we can fix that by really helping scientists to be visible, not just through publications, but also through publishing data sets, to doing data curation work and being rewarded from that. And by collaborating digitally through a network of fair data sets. And open science and fair data, I think, really offer a way forward for society as a whole. Okay, so these are really nice claims in story, but can I back it up? That was also part of the text that was the basis for this webinar. So I highlighted one sentence from there. Are we really sharing health data on a global scale to improve medical practice? Can I give a concrete example? And that's what I would like to do next, and posit that yes, also medical evidence generation is changing through open science. So let me take a step back. We're in the context of health data networks. What are we talking about when we say health data networks and health data? Before I really go into medical evidence. So a couple years back, I had this webinar where I defined health data, and I think many people before me did it exactly the same way. It's, if you really drill it down to the absolute basics, it's some way of exchanging health data between three classes, which are the scientific researchers and medical researchers, the citizens or patients, and then the healthcare professional and the whole sort of hospital and medical world. And these three classes of actors come together in all kinds of ways. And indeed, the problem of health data is that there are so many different types of health data. So if you think about the Seneca network, for instance, we have longitudinal cohorts in our network where people are being followed over a longer time. But you can only have a few aspects of data in such a data set. And in reality, if you talk about the medical evidence as a whole, you ideally should be able to account for all these views. You know, it's the clinical view from, let's say, in a hospital context, that would be systems like the EMR with medical records, the laboratory information management system, imaging systems, where we have the CT scans and the MRI scans, etc. It's the clinical guidelines and the typical classical treatment pathway. You know, for instance, for prostate cancer, that starts with a biopsy, and then there's a PSA measurement, and there's a Gleason score, and based on these numbers, doctors will go one way or the other, and they will prescribe different medicines and recommend different interventions. So that is the clinical view, and in this actually goes back all the way to for instance, for cancer, with the first clinical trials, is to try and understand what is the disease exactly, and how can we modify it, and how does it present itself to me as a physician. Then, of course, there's also a molecular view where we can measure so many things now. I've heard it say that SARS-CoV-2 is now the most sequenced organism on the planet. I will believe it, but of course, even for humans, if you think about some of the members we have in Sinica, like Genomics England, for instance, they have been measuring DNA of people for a number of years, and with the data that we get from DNA, from the RNA, from looking at the proteome, the metabolome, even the microbiome, epigenome, etc., we can get a lot of information on how we think that the molecular mechanisms and the cellular mechanisms behind those clinical phenomena are. And there's an interaction between them, because sometimes the same clinical presentation is very different underlying molecular mechanisms. Another important part of this, of course, is the drug discovery, where we look at the effect of drugs and how we can modulate the molecular pathways. Then there's the financial view, and I'll give an example of using this kind of data as well, where we show the patient as a customer going through a health system, for instance. So we have claims. Nowadays, there's a switch to value-based healthcare, where GPs or well, GPs, it's already for a longer time, of course, but even in most health systems, this is not really used, reimbursing based on the outcomes rather than on the procedures or drugs given. And this introduces some interesting incentives. And then there's the whole health economic space, where we try to follow patients as they go from different disease stages and understand the economic impact of reimbursing a certain treatment. And perhaps the most important view is the view of the patients itself in the end, which has lately become, also because of the outcomes-based measurement trend, more important, where we are asking also the patient for what is your own assessment of your health status. Now, I could go on with this, there's a legal view, etc. But I want to point out something else, because even with these different data sets, our data sets often take one of these views and then an incomplete ones. And so one of the biggest problems that we have is establishing causality. I'm currently reading this very interesting book, which I can definitely recommend, on causality. It's called The Book of Why, by a data scientist called Judea Pearl. And I think he goes a bit far when he almost suggests that causality is very new in science, but yet a mathematical description of it is a recent phenomenon. And our brain works that way. If I look at my 2-year-old daughter, she constantly reasons about causality, but we have had a big tendency, and still have in statistics, to only limit ourselves to speaking about associations. Yeah, there is some sort of statistical correlation and not actually causation, but causation is important. If we know what causes a disease, or only if you really understand, for instance, how a disease like SARS or how a virus like SARS-CoV-2 transmits itself, you can reason about, okay, what can we do to limit the transmission? A concrete approach that I would like to present as an example of the medical approach is the Odyssey approach. So Odyssey is one of the open source communities that the Hive is engaged in, and it has the OMOP common data model. And the problem is, with all this health data looking so different, and claims data sets, EMRs, cohort studies, if you want to do medical research, you run into this problem. You have all these different data sets that are not easily harmonized. And if you want to do a rigorous analysis, you have to standardize it in some way. So that requires data interoperability, where we use the same terms for data, and also make sure that the syntax of the data is the same. I'll show that in a minute. We also have standardized analytics. So in order to be able to compare across studies, it's important that you use a comparable analytic setup. Then, of course, a data network where there's a growing community of people that harmonize and standardize data in this way, backed up by a community of data experts, clinical experts, statistical experts. And indeed, if you do all that, then it becomes easier, almost as easy as just plugging in your standardized analytical method to the data and getting the results. And indeed, this is what the Odyssey community has shown and is increasingly successful at in the medical world. So the OMOP Common Data Model is, I would say it's based on the standard health facts that exist in most of these sources that I named. I mean, claims data and let's say cohort data from Genomics England look very different, but what they have in common is that there is a person. That person has potentially drug exposures. It has procedures that are applied. It has conditions that are described, and it has measurements. And all of these have their own vocabulary. So conditions would be in SNOMED CT, for instance. Drugs could be in RxNorm or ATC. Measurements could be coded in LOINC. And an important part of the Odyssey community and OMOP standardization is to have all these different, often local coding systems. You can see here a Japanese, UK, but also global coding systems, and map them to these standards. Another part, as I mentioned, is standardized analytics. So in medical research, often a number of, certainly in observational research, a number of specific statistical methods are used. And it's helpful to standardize those so that the results become comparable across multiple analyses. And of course, as I mentioned, a network is important. And one such network, I already mentioned the Seneca network, but there's also an EDEN network, where the EDEN network is a growing set of European healthcare records. We already have more than 200 million patient records combined. And often these are through hospitals, but also GP practices coming together. And we use OMOP as a standard there to map the data so that we can run distributed analytics. An earlier example of such a study is this study, which was looking at antihypertensive drugs over millions of people throughout the world. And there were some interesting findings. So for instance, the thiazide diuretics had fewer adverse outcomes than ACE inhibitors, even though ACE inhibitors are often prescribed. But what makes the study most interesting is the way in which the data was generated. And that is explained in this paper with the legend principles. I won't go in detail through it, but just to give you a flavor of it, it's about generating evidence at large scale. So instead of looking in one data source, which also has its advantage, but if you really want a signal, it's useful to have multiple databases throughout the world. And looking not just at one drug, but a class of drugs. And not just at one method, but a class of not one hypothesis, but just generate all the hypotheses that you can from a certain set. And here on the right, you can see the diagram for this. So you start with defining the research question properly. And then yet another principle is, first you define your analysis, and then you publish your analysis, and then you run it. This is very important in epidemiology, so that you're not falling in the trap of cherry picking your data and your results. All right, so that is an example of an approach through Odyssey of how medical evidence generation is changing through open science. Open standards, interoperability, global networks, and even standardized analytics. And instead of just doing one hypothesis in one database, studying multiple hypotheses in multi-databases at once to do it at scale. All right, but in the webinar, text, I also said that I raised the question whether COVID-19 has somehow changed this, and has the situation actually improved? What I will say, and I'm happy to hear your views on this, is yes. Overall, I think the COVID-19 pandemic is an accelerator, certainly for open science. It maybe exacerbated a little bit the bad and the good. But if you look at the flurry of activity, especially in bioinformatics, right? So bioinformatics traditionally has a focus, I would say, on fair and making data available to the world and sharing data. Much less so than maybe the medical science community. But just one expressive example that I saw was NextTrain. And NextTrain was already there before the coronavirus pandemic started, but they had all the things in place to very rapidly scale up. And I think what is now an unprecedented level of being able to compare strains and variants throughout the world. You also saw a very big rise of citizen science and hackathons and study-zones and the like popping up everywhere. Here it says the top 10 hackathons in May. I haven't done a comprehensive survey, but I would estimate that there are thousands, probably tens of thousands of scientific hackathons, meetings, where people really focused on trying to do something with COVID, even data scientists that had never before worked with this type of data. And I would argue that that's a good thing. But of course, it comes also with challenges. However, what about the medical science? I want to give an example again from Odyssey. So building on what I just explained about it, in March, there was a studyathon around COVID from Odyssey, and there were 37 healthcare databases involved, where there were COVID patients present. Here's just an example from one study where we looked at several data sets in the United States, in Europe, in Korea, and Japan. And the idea here, as explained before, is that the data stays where they are, but is mapped to OMOP, so to the standard model locally. And then at the same time, or actually later, an open source analysis code is produced. And that's the main part that's going on during the hackathon. And once you've established the code, and thanks to the standardized model and the analytics, this can literally be done real time in the course of a few days. This code is executed and the results are being published. In fact, there were 12 different questions that were studied in this studyathon, and most of them have already resulted in papers. One example was about the safety of hydroxychloroquine, which was a very big pressing question at the moment because it was advertised as a safe and effective medicine. And so the safety was looked at in more than 1 million people that used this drug worldwide. So this drug was not very well known, mainly prescribed for rheumatoid arthritis, but suddenly became very much a matter of debate. And so by being able to leverage the OMOP data and the analytics that the Odyssey packages have, really in a few days, this study was performed in more than 1 million users of the drug worldwide. And that went on to inform, for instance, guidance from the European Medicine Agency on the use of the drug in relation to COVID. And as you can see here, there were a whole host of preprints just from that one meeting. And interestingly, going back to my earlier point from the role of publications in a peer review process in science, which I think is very important, but is also sometimes frustrating to be part of. It was really only months and months later that the peer-reviewed articles appeared. So to tie back to my original slide and opening of the webinar, the question about how angiotensin receptor blockers and ACE inhibitors really interact with COVID-19, we try to answer that in this article using the Odyssey standardized analytics. So one of the co-authors of that article, and have kind of monitored the whole progress from an open science and fair angle. And I think that this way of doing analysis should become more common in the medical community, and indeed will become more common. So more study-a-thons are on the way. In addition to the hackathon from Seneca that Marta mentioned, here's another one from Pioneer that goes into looking at prostate cancer data. So you're welcome to check that out if you want to be part of something like this. So to summarize my third point, I would like to state that in my view, COVID-19 pandemic is an accelerator for open science, and that scientific communities have come together in unprecedented ways. However, we also have seen, and I think this was very readily apparent in many of the health systems, for instance, with the COVID-19 case counting, is that getting data out of the medical system, whether that's just clinical data or financial data, or increasingly also biomolecular data, is extremely hard. And this is also one of the challenges that we try to address by the framework we're setting up in Seneca, as Marta explained. So in summary, I have told you a little bit about open science and the role of the FAIR principles in this, about how medical evidence generation is changing through open science, and about the COVID-19 pandemic role in that. And I'd be very happy to discuss further with you and take questions or comments on this topic. Over to you, Marta.
Thank you very much, Kees. So we are now opening the floor for questions, and as I told you, you can write them in the question section of the GoToWebinar, and then we'll read them up for you. Oh, there's already one coming, Kees. So they say, thank you for the presentation. What is the status of the standardization of FAIR principles? Is it comparable to, let's say, ISO standards? Also, to what extent the verification practices are area agnostic?
That is a very good question. It's definitely not ISO material, and I don't think it ever will be, because the FAIR principles aren't, well, they're aspirational in the first place by the authors. So the intent was always to set a bar that wasn't easy to meet. And the joke is, you know, if something is 100% fair, then we should just raise the bar for fairness. But it is an important sort of technical aspect about fair digital objects, which is measurable. So you can, for instance, from a machine readability perspective, you can establish whether a data set has indeed identifier, is using standards. And so perhaps with those more technical aspects of the digital object, so which is a slightly narrower set of the FAIR principle, there is a possibility to go for something like an ISO standard. Maybe even more important, in my view, would be not to have necessarily an ISO standard, but a pragmatic web standard. There are some competing models for metadata, for instance, out there that are getting traction. I'm thinking about something like schema.org, which is used on the web to make resources findable, not just on science, but on anything. And there are other ways to provide standardized metadata. For instance, a very old standard that's still highly active and applicable is the Dublin Core Metadata Initiative, DCMI, who has also some candidate properties, let's say, to make it comparable to ISO level standardification. So that's the standards aspect of your question. You also asked something about, is this domain specific? Part of it is very domain agnostic. So the fact that the data set needs to have a persistent identifier and that there's a global object, this can be standardized. And you know, some organizations like the nonprofit DONA Foundation, for instance, is looking at that. And also in the FAIR world through GoFair and DTL, we have some activities going on. And if you're interested in that, you should look for the term fair digital object. But other aspects of the FAIR principles, for instance, the FAIR principle R1.3, which is about meeting community standards, are sort of inherently very domain specific. And in fact, I think the most useful way to look at verification is through the lens of a certain domain or community. And this is also the way the GoFair Foundation is set up. Because chemistry community should decide on what is important metadata for chemistry. And a biology community, and indeed the subdisciplines there, can decide best what is important to share and standardize for biology data.
Thank you very much. So there are quite a few questions coming in. So I'll read the next one, and I hope I don't mess too much the acronyms. What lessons do you think other communities can learn from the EDEN network on the importance of a common data model like OMOP or OMOP, and the challenges and practicalities of encouraging adoptions?
Yeah, again, a very good question. So there's the theory of how data networks, and then there's the practice of it, right? And the way I view the Odyssey community, because I'm involved in multiple open source communities, and every community has their own way of addressing it. I think that OMOP can be characterized as being very pragmatic and also being quite epidemiology driven. So, you know, the clinical and the statistical people have a big voice there. But the IT aspects and all the informatics aspects of standardizing the data in OMOP are super pragmatic. Even the model itself isn't, you know, it's not nearly as formally specified, for instance, as OpenAir or even FHIR. FHIR is also much more semantically specified than OMOP. So from the FAIR principles perspective, those are things that can be improved. And in fact, some of my research focuses on how Odyssey could improve this. But perhaps the most important lesson here is that you do need to be pragmatic, because even though the tools that EDEN and the Odyssey community provide to data owners are simple, you know, we have tools like Whiterabbit, which is just you can use it on any database, and it will generate an Excel report, well, a CSV actually, of how your data looks like and what are the most common terms in there. And then you can plug it in another tool which tells you which of those terms already exist in the OMOP vocabularies. So very practical tools, and I think that really made the difference. Together with the EDEN Academy, which explains how all these tools work to the average IT administrator in a hospital, for instance.
Thank you very much for the answer, Case. So another question is, well, it goes preceded by amazing talk. Then I want to know how the developing countries can contribute to these initiatives. Do you know some organizations or institutions in Latin America that work on FAIR?
Yeah, that's a very good question. Certainly in Latin America, there is activity around FAIR, and by the way, also around Odyssey. I would think that perhaps a better person to answer this question that comes to my mind is my colleague in DTL, Luis Bonino. But the GoFair Foundation, if I'm not mistaken, has actually an active node in Brazil. So that would be something to check out.
Thank you. So next question, could journals and grant providers recommend or enforce fairness?
Yes, of course, and increasingly they are doing that. So, for instance, the Nature has put out the Nature Scientific Data is the paper where originally the FAIR principles were published. But Nature as a journal also encourages implementation of FAIR. And a lot of the European funded research is mandated to have FAIR output. the way in which this is materialized right now is often that it's mandatory to create a data stewardship plan, which explains at the beginning of the project. So you think before you do your research and your analysis, you think about all the aspects of FAIR. How will I publish my data? What repository can I maybe use to disseminate the results? What are some of the appropriate standards that I can use? And a website like fairsharing.org can be used to find the standards of interest that you could use. The data stewardship wizard is another tool that's very helpful to create such a data stewardship plan, as it's called. So yes, journals and funders are mandating FAIR. It's not just European Commission, it's also NIH and G7 to G20 have kind of put out statements that as a countries, they think it's important to strive for fair data. But really the proof of the pudding is in the eating. And also on the previous question, I think that making the standards really fair and explaining how you do things is how we can globally drive this forward. Because if we look at the demographic, sorry, this is a bit of a side track maybe, but if we look at the demographics in Africa in the coming decades, and if you even today look at GitHub, how the activity is kind of shifting over countries, it's clear that 10, 20 years from now, there will be dramatic shift in where scientific contributions and where data is generated. And we can anticipate by that through using open and global networks, exactly as FAIR advocates.
Thank you, guys. Now that you mentioned that, do you think that's how it's gonna move? Like, new people are gonna start using it more and more, and we will have more open science? Or do we need a lot of, how to say, targeted campaigns to promote it and having all the journals asking for it or things like that?
Yeah.
So how natural or targeted it needs to move?
I think both are very important. To have a bottom-up focus on, for new people coming into the field, make sure that things are fair by default, so to speak, and that we think, data stewardship plans should be a no-brainer for any PhD. And in fact, sometimes I always really like to do classes and to work with PhD programs, for instance. And when I show the data stewardship wizard, typically almost none of them have heard of it. So we may think that the FAIR principles are visible because fund is mandated, but it doesn't mean that scientists in their everyday life have actually heard of it. It's probably even a small percentage today. So that is very much needed, the bottom up, but the top down also, because, and I think some of the funding there is helpful, and Seneca is just one of the many projects where we can work on this. Making data fair and figuring out how to do this is not easy. I've now done a few analysis and projects where we just took one specific data set and went for like maximizing the fairness. And then you realize that you're spending hundreds and hundreds of hours on that one data set, which is very disproportional, certainly if you do that after the fact or retrospectively. So what's needed is for people on the vanguard of FAIR to think about is do this once and show that, for instance, like Odyssey has done for medical studies, and maybe Nexttrain and the community around it has done for how do you publish the genetical makeup of viruses. Every community should have this vanguard of thinking about how do we make things fair so that others can benefit from that. And that's also where some of the funding for FAIR is very important.
Thank you. So another question, a more specific one. How can we make use of machine learning techniques such as, for example, NLP to partly automate data curation?
Yeah, that is another active area of research. of course, the problem with NLP and with deep learning techniques is that you often need a sizable training set, which covers enough of the space of the parameter space so that the model can actually learn to map data. And to do that for health data is an active problem. Another sort of related topic that I'm interested in, and we have a PhD student at the Hive working on that, is the synthetic generation of data. So, for instance, you can use generative adversarial networks to try and produce lifelike health data. If you have enough real health data, you can perhaps train a network to pick up the latent signal or logic in the data sets, and if a synthetic generator could produce data that is not distinguishable from real data, that would be super useful, because that would sort of alleviate some of the privacy constraints that we have and still allow us to do research. But yeah, these are active topics, and so far haven't yet yielded a clear result, other than maybe tagging. I guess the imaging field is that's not NLP, but in the imaging field there is a very clear move for AI on recognizing images. And in NLP, the thing that we are doing now at scale, or many hospitals are doing, is indexing medical text from the EHR medical records and annotating that with the right terms, so that you can at least automate the searchability of those.
Thank you. So let's go for the last question. How rigid are the FAIR principles, considering open science could foster novel ideas which might complement or question these principles?
Yeah, well, I think if you ask anyone in the FAIR community, that the FAIR principles should be considered a living thing and not rigid. And indeed, they are just meant to spark a debate and spark a new way of working. And I think they definitely have succeeded, at least to some extent, in that, if you look at the uptake over the last few years. Never as some sort of standard that needs to be met for formal reasons, really. The goal is here for the FAIR principle to be an accelerator towards where we really want to go, which is open science. So if open science bring new insights that would cause us to change the FAIR principles, yeah, without a step, I definitely we should immediately do that. That's a no-brainer. But I think they're fairly generally applicable, the FAIR principles, and as explained, they're also not covering the whole space. Data stewardship as a whole and open science are the things that really what matters here.
Thank you very much, Kees, for the amazing talk and the insightful answers to the questions. I think we are going to close soon. Can you go to the last slide just to remind about the next webinars? So as I told you, this is the introduction webinar to the How Fair Are You webinar series and hackathon. So I here added the two next ones, which will be on making cohort data fair on the 10th of February and on FAIR software tools on the 24th February. So please visit our website and register there if you want to join us for the webinars. So thank you very much all for your attendance, and we'll post the slides and video in the Syneca website and YouTube channels.